All right, let's talk about the alternating series remainder. We said that the remainder, the error in approximating if we stop at a certain number, is always less than or equal to what that next term is in the alternating series, regardless, like ignoring the alternating part of it. So the error is going to be less than or equal to the next positive portion that's either added or subtracted here. So let's look at a couple of examples and apply this. So considering that alternating series we did on the previous example, suppose we find the fifth partial sum. So the fifth partial sum, let's see, we'll start at 1. That's 1 over negative 2 to the, 0 plus 2 over negative 2 to the first plus 3 over negative 2 squared plus 4 over negative 2 cubed, and 5 over negative 2 to the fourth, which would give me 1 minus 1 plus 3/4 minus 4/8 plus 5/16. So that fifth partial sum would be, let's see, if we 12/16 minus 8/16 is 4/16 plus 5. So we have 9/16 is the fifth partial sum. Now, because we added last, you see how we went from 1, when subtract 1 back to 0, up to 3/4, and then subtracted a half, and then we added 5/16. So we started at 1, then we subtracted 1 and got 0, then we added 3/4, subtracted a half, so it would put us at a quarter, added 5/16, and so we're narrowing in. We're a little high right now, though, so we have some error. What we can do is just look at what the next subtraction would be. So a sub 6, the next one would be 6 over 2. I'm going to ignore the negative part here. 2 to the fifth. That's 6 over 32, or 3/16. That's what we would subtract to get below. So we know our error has to be less than or equal to this. So what we could say is that the sum, the full sum, is equal to, well, actually, it's not equal to, is between, now because the 9/16 ended up above, we could say it's between, let's see, if we subtracted 3/16, it would be between 6/16 and 9/16. Right, 9/16 is definitely too high because we stopped right there. We're going to subtract something. We're definitely too high. If we subtracted 3/16, we're going to be too low. But we know it's going to be between those. So our error, the real, what is the maximum error, is really 3/16. But we know that this full sum was somewhere between 3/8 and 9/16. What if we wanted to be within 10 to the negative sixth? The key here is that partial sum is the sum, let's see, let me use S sub k. So it's the sum k goes from 1 up to n. N goes from 1 up to k. So the partial sum, S sub k, would be going up to the kth term, n over negative 2 to the n minus 1. And the error is always the next term. So a sub k plus 1, that next term. So that would be k plus 1 over, and I'm going to ignore the alternating part of it, so just go 2 to the k plus 1 minus 1, which is k plus 1 over 2 to the k. Now we want to know, we want this error, we want it to be less than or equal to 10 to the negative 6. So, or actually less than, we want it to be less than 10 to the negative 6. And so, you could try to maybe set these equal to each other and solve with some technology. This particular one you could guess and check. It's not a trivial thing. I would probably use some technology, set those equal to each other and solve, and then round up, because you're going to have to round up to the nearest, right, because we just have 1, 2, 3, 4, 5, etc. So, and then in fact, k is 25 is the first one. Maybe we say k has to be at least 25 to have an error less than 10 to the negative 6. So that means we would need to have, or is it 25? Yep, so we would need 25 terms. All right, this fourth one here, this is kind of hard to believe. We're going to prove this actually in like 3 or 4 weeks, that the sign of a number, in this case the sign of like 1/10, is equal to, in fact you can write it this way, sign of x, any number, is x minus x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th over 7 factorial, etc. Seems a little far-fetched. We will get there. But here we have an alternating series, right? Plus, minus, etc. The formula is a little funky. You can see the factorial. It's kind of weird because it's skipping, right? It goes from 1 to then to 3, no 4, 5. We'll learn how to do that right now. It's not really important. We want to know how many terms are necessary if we want to approximate this within 1,000th. So the key here is that the error is always less than or equal to the next term. So let's start looking at these terms and see, well, what if we just stopped here? The error would be less than or equal to the 10th cubed over 3 factorial. But this is crazy. A 10th cubed is actually 1,000th over 6. So that's a 6,000th. That's already less than 1,000th. So believe it or not, sine of 1/10 is actually equal to a 10th within an error of 1,000th. That's pretty cool. So that's kind of, again, it's a little far-fetched, but we will get to this. But here's an example. The key here is this is an example of an alternating series. It alternates plus minus. If we want to know, we want to approximate it within the 1,000th. That's the error. We want to be within that, so that's the maximum error that we want. The error is always less than or equal to the next term. So if we stop right at the first one, the error is less than or equal to the next one. And so that's it. So how many terms are necessary? Just one. All right, that's it for this one. We'll do the next page in a separate video.